Hello there, this is our video on Erwin Schrödinger, and look at him, he's just as happy as you are because this is our second to last video on atomic scientists. So please take out your handout so you can start taking notes. Erwin Rudolf Joseph Alexander Schrödinger, yes, that's his complete name, very long, was born in 1887 and died in 1961 in the city of Vienna, Austria. Schrödinger lived in many different countries in Europe. In 1921, he moved to the University of Zurich. In 1927, he succeeded Max Planck at the Friedrich Wilhelm University in Berlin. Then he had to leave Germany because he disliked the Nazi regime. He moved to Oxford, and soon after he arrived there, he received his Nobel Prize in Physics in 1933 for the discovery of new productive forms of atomic theory. In the first years of his career, Schrödinger became acquainted with the ideas of quantum theory that were developed by Max Planck, Albert Einstein, Niels Bohr, and others. He also worked with Wolfgang Pauli in the 1920s when he moved to Germany, and that's when he wrote his first publications on atomic theory of spectra. In 1926, he presented the Schrödinger equation, and this paper was universally celebrated as one of the most important achievements of the 20th century, created a revolution in quantum mechanics and indeed in all physics and chemistry worldwide. So this was a very important achievement for Schrödinger. An interesting fact about Schrödinger that I didn't know was that he wrote a book titled What is Life? And in this book, he addressed problems of genetics. And then, according to James Watson's memoir, Schrödinger's book gave Watson the inspiration to research the gene which led to the discovery of the DNA double helix structure. So I thought that was very interesting how all these scientists are interrelated with one another. To talk about Schrödinger's work, first I want to explain Schrödinger's cat-thought experiment. To explain Schrödinger's cat paradox that was introduced by him in 1935, first we have to start by explaining the Copenhagen interpretation of quantum mechanics because the cat paradox is a reaction to this interpretation. So, according to the Copenhagen interpretation of quantum mechanics, which was devised by Niels Bohr and Werner Heisenberg, quantum mechanics does not yield a description of an objective reality, but it deals with probabilities of observing or measuring different aspects of the energy levels. Now remember, these energy levels do not follow classical mechanics, they are quantum mechanics. Classical mechanics applies to objects that are big enough, for example, like the planets, but when we move to a molecular level, we cannot predict, for example, the movement of the electrons in the atom using the laws of classical mechanics. So this is when we start having problems. Now, the act of measuring causes the set of probabilities to immediately and randomly assume only one of the two possible values. And for the electrons in the atom, we have the uncertainty principle proposed by Werner Heisenberg, in which we can only know the momentum of the electron or the position of the electron. We cannot be sure or certain about both of these values. We can only know one. So that's when Schrödinger comes up with this cat paradox, and I love this cat. It looks just like my cat. This cat paradox states that the cat may be both dead and alive depending on a previous random event. Now, how can a cat be dead and alive at the same time? That's crazy, right? Well, this is what happens. We have radioactive material here that has a 50-50% chance of breaking, I'm sorry, of triggering a Geiger counter. Then, if the Geiger counter is triggered, the hammer falls, which will break the bottle of poisonous gas that will kill the cat. But if that doesn't happen, then the cat is alive. Yes. So this is something that's very confusing to understand. So here we have an explanation for that. While the box is closed, the system simultaneously exists in a superposition of states. That means that we have a superposition of the cat being dead and alive. Now, only when the box is opened by an observer and the observation is performed, do we collapse? That's when we collapse the wave function into just one of the two states, like we have with the electron. Either we know the momentum or the position. So here the cat will be either dead or alive, which is something that we're expecting, right? So I will show you a video that better explains the cat paradox, so you can actually see like what is happening at the same time. And I thought that this video was very cool, so hang there, let's see the video, and then we'll come back to explain Schrodinger's atomic theory and his model.
Welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrodinger, who helped piece physics back together after Einstein and his crew blew a giant freaking hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. So I have to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrodinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrodinger? This is not the best way to get people behind the idea of funding the sciences. So, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time, because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws, so it, just like every other cat in history, is either alive or dead. Schrodinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other
Based on that, here we have Schrodinger's proposal for the atomic model. We have a nucleus which is in the center, and this nucleus is surrounded by an electron cloud. So we totally dismiss the orbital. Now we have a cloud, and the cloud represents the probability of finding the electron in a certain position. Now we will never know for sure where the electron is. What we can only do is calculate its probability of finding the electron in a place within this cloud. The darker spots represent a higher probability of finding the electron in the cloud. So here we could find the electron. It has a higher chance, however, we will never know if the electron's there. Yeah, so these are only probabilities, and that's the concept of quantum mechanics, quantum theory. We will never know for sure both the position and the momentum of the electron. So if we calculate the momentum, then we don't know the position. And if we calculate the position, we don't know the momentum. And here is the atomic theory that Schrodinger proposed. So this is also known as the quantum mechanical model of the atom. And for number one, we have that the atom is a nucleus surrounded by an electron cloud, which we already saw. Number two will be uh, the exact path of the electron is not defined, so we cannot talk about an orbital because this orbital is not defined. We just talk about an electron cloud. Number three states that where the cloud is most dense, the probability of finding the electron is greatest. And this model predicts the odds of an electron's location. Again, we will never know for sure. The only thing we can do is just calculate the probability. And the probability for calculating that, what we have to do is first solve Schrodinger's wave equation, and then we would have to square the equation to calculate the probability. That's a lot of math. We're not going to do that. But what we want you to know is Schrodinger's atomic theory and the model of his atom. So that's it for now. Thanks for watching, and I'll see you in class.